All right, so I went ahead and drew the circle. So I told you S is 300 miles, but you got somebody running around the circle for 300 miles. The radius of the circle is 11 miles. Yesterday, we found the question, or we answered the question, how many degrees does this runner go through? So today we're looking for how many laps. So there's three different ways to measure, how many times you go around. You can measure the angle in degrees, like we did yesterday. You can measure the angle in radians. And you can also measure the laps, the number of rotations, right? Same thing. So we're going to pull out our handy dandy formula. And now my pencil is not synced. Man. My iPad is acting this week, kind of like my heat pump outside was acting at this time last year. And my pipes were acting. We were off this time last year, right? It was like the snowstorm. Yeah, so thank goodness. Okay, there we go. So S equals R theta. And let's plug in. We got 300 miles. We'll put that in there. The radius is 11 miles. And we got times theta. So if I solve for theta, it's going to be 300 divided by 11. And the miles are going to divide out, right? So that's going to give me radians. Now, I don't want the answer in radians. I want the answer to be in what? Rotations. So you don't have to convert it to degrees before you go to rotations. Let's put this over 1, and we're going to multiply by a conversion factor. I want radians to divide out in the bottom, and I want rotations or laps to appear in the top. So 1 rotation is how many radians? 2 pi, right? 2 pi. Now, all we got to do is type this in. 300 divided by 11 divided by 2 pi. Now, I wish I can show you, but it's not going to happen. So here's what you need to do on your calculator. Most people, when they type it in and get it wrong, it's because of this right here. So what you're going to want to do is type it in like this. You're going to want to do 300 divided by 11 divided by 2 divided by pi, or 300 divided by 11 divided by parentheses 2 pi, okay? Either one of those. If it's a factor in the bottom, you divide by it. Here's what you do not want to do. This is no. Don't do 300 divided by 11 divided by 2 pi. Because in your mind, 2 pi is a singular quantity. But in your calculator's mind, it's not. So if you do it this last way, it's going to divide by 2 and multiply by pi. And we're testing tomorrow. And you're going to have a question like this. And guess what? One of the answer choices will be, it'll be the answer you get when you type it in like this third line and you divide it by 2 and multiply by pi accidentally. And you're gonna be like, oh yeah, there's my answer. Boom, I got it wrong. Okay, so it doesn't matter which one of these you do. It probably makes more sense for y'all to do it on the second line. So let's see if we get the right answer together. All right, 300 divided by 11 divided by, I like to do divided by 2 divided by pi. It saves 1 keystroke. And I get 4.340 or 4.341. And that'll be laps or rotation. Remember, we do need that 0 if we truncate, because it's not terminating 0. So on your answer choices tomorrow on the test, I may decide to round, I may decide to truncate, right? Either one. I made the test last night while I was sitting in front of my computer. That's where I typed it up. So anyway, if you want to know where you can go to practice, I will tell you what I did, since now we're warm. Any questions on the warm-up? Okay. If you want to practice, here's where you could go. You could go to Corpy's World. There it is, Corpy's World. And of course, you go to Precal Matters, because it does. And you go to, of course, oh, speaking of YouTube, today in 2005, YouTube was launched. And one of the inventors of, or founders of YouTube, had the first video. I think he was at a zoo and he's like, dang, that's some big elephants. And that's the whole video. That was the very first video. Look it up on your own time. I wish we had time to look it up together. But anyway, if you go to the old tests, we're testing over 5.1 to 5.2. And notice there's only one test out there so far that covers 5.1 to 5.2, and it's from 2014. And I have the answer key there that has not only the answers to the multiple choice, but it's all worked out. I literally had this test in front of me while I made the test. So I went through and I was like, yeah, I like that question. I liked all the questions except one of them. One of the multiple choice questions I changed. And the one that I changed it to a question like the warm up. Oh, how about that? Yeah, yeah, yeah. So, yeah, you're welcome. So the only difference is I'm going to shuffle the questions around. So the question that's similar to number 2 on this test might be question number 3 or something like that. But that's it. So as you're preparing for the test for tomorrow, you might want to work 2014. Now the worksheet from 5.2, I'm not going to make you turn it in because we're not going to do everything. We're not going to do all the questions. So you don't have to turn that in. I'd rather you turn in your notes at the end of today, and then tonight, instead of completing the worksheet, I'd rather have you go sit down and work that 2014 test. Sound good? All right. So, all right, that's on video, so it's now official. And let's see, is it still loading? We'll try this again. No. Okay, so we're not even going to bother with that today. All right. So let's get back to what we were doing yesterday. We were trying to determine what the perimeter square footage and all that stuff was. So I'm sorry. Yeah. Okay, good. So let's do part B. We want to know what the area. We want to know what the area of the slice is. So remember the formulas that you're going to need to know that I'm not going to give you are S equals R theta. That's what we did on the warm up. And then the area of a sector is 1/2 R squared theta. I'm not going to give that to you either. And in both cases, theta is measured in radians, in both cases. So we're on part B. We want to figure out the square inchage, if you will, of the face. So remember the angle theta was 40 degrees, and we converted that yesterday, and we got 2 pi ninths, I believe. Is that right? Can someone verify? Yeah. Okay. So and then the radius of the pizza was 7 inches. So now we just plug it in. So the area of the slice is 1/2 R squared. So that's 7 inches squared times theta, which is 2 pi ninths radians. And again, I'm including units because I want to check to make sure my answer is right. So I'm expecting to measure area in square inches, and I get inches times inches, which is inches squared, times radians, which is unitless. So I do get inches squared. Now, there's 2 different ways we can give the answer. Depending on how I was feeling last night, I may give you answer choices that are exact answers in terms of pi, or I may give you 3 decimal approximations. So let's do it both ways. Because remember, it's customary to always give a simplified exact answer first, and then a 3 decimal approximation. So to type this in, I'm going to go 0.5 instead of 1/2. 0.5 times 7 squared, or 49, times 2 divided by 9. I'm going to leave the pi out. And I get 5.44444. Okay. And now I'm going to convert that to a fraction by hitting math, enter, enter. Math, enter, enter. You get 49 ninths.
Yeah, because I did it with the fractions.
Oh, that'll work too. Yeah, if you use the horizontal division bar, you might get straight 49 ninths. So one version of the answer is 49 ninths, but remember pi is still there, square inches. So that might be an answer choice, right? I may give that as one of the answer choices. But in reality, if we're trying to get a feel for what that is, we prefer it in decimals. So now if you just hit times pi, you get the equivalent, which is 17.104 square inches, either way. All right. So pretty simple. The key is you never use an approximated answer for a subsequent calculation, and your angle has to be in radians. Now, I'm going to add one more little question to this. If I want to figure out the volume of the pizza, all we have to do is multiply by the 3rd dimension. So let's say that this pizza is 3/4 of an inch thick. Okay. For the most part, this pizza is kind of like a polygonal prism. And all you have to do, remember from your star test or whatever, is you take the area of the base or the face and you multiply the distance between the top face and the bottom face to get the volume. And so if we know the area of the face, which we just found, all we got to do is multiply it by the thickness to get the volume. So take your answer from the previous line, 17.104226667, and just hit times 0.75 or times 3 divided by 4, and you get 12.828. So that would be the volume. So for what it's worth, the volume of this slice, which is the true measure, I'll just show this. It's the area times 3/4, so that's 12.828 cubic inches. That's the true measure of the space that it takes up in Mr. Kilford's stomach. Now, I looked it up yesterday. The average human stomach on the lower end has a capacity for about 120 cubic inches. 120 cubic inches on the lower end. So assuming he doesn't imbibe any fluids, Mr. Kilford could eat about 10 of these Freudian slices in his stomach, right? But as Brady pointed out yesterday, the pizza only comes with 9 slices if they're all 40-degree angles, right? So he's going to have room left over by scarfing the whole pizza. He'll have room left over for like a Piaget and Pepsi or something, right? Although he wouldn't drink, he wouldn't drink Pepsi because his wife works for Coke. Yeah, so he would drink like a Carl Jung Coke, right? All right. All right, cool. So any questions on that? Pretty easy, right? If you memorize the formula and you know you're in radians, pretty easy. All right, I'm going to skip this, but the compass rose, it's one way to navigate. Most people know north, south, east, west. But if you come in at a 45, you have your northwest, northeast, southeast, southwest. But you can even divide those. So like if you look right here at this yellow one, we would read that the little b means by. So this would be west by south, southeast by south, so on and so forth. So the only difference is when you navigate using a compass rose, planes usually go on headings and ships usually go on bearings. And if you superimpose a coordinate grid on top of north, south, east, west, we always start due east and our positive is going upward, right, towards north. But whenever you are on a heading or a bearing in navigation, they always start 0 degrees up at due north, and the positive rotation for them is towards east, right? So if a plane is flying on a heading of 90 degrees, for us, 90 degrees would be flying due north, right? 90 degrees is straight up. But if a plane is on a heading of 90 degrees or a boat is on a bearing of 90 degrees, they're actually going due east. Okay, so same 360 in one rotation, just starting at a different place and rotating a little bit differently. So I'm not going to ask you anything about that on the test. Just be aware if someone tells you they're on a heading of something, you know, you don't want to be going the wrong way, right? Dude, I went this way and you went that way. It's like, yeah. Okay. Angular velocity. Okay, so maybe you've had this in your physics class, but once something rotates, we can measure how fast it rotates. Just like when something changes its horizontal position, we can measure how fast that horizontal position is changing. We call that linear velocity. And we measure that in distance units per time, like feet per second or miles per hour. But when something rotates, we can measure its angular velocity. And we measure that in units of rotation per units of time. So that would be like revolutions per minute, rotations per hour, degrees per second, radians per day, right? Any units of rotation, which would be degrees, radians, or rotations per time, okay? So to measure angular velocity, we use the lowercase omega. So here's capital omega, omega capital. And then the lowercase omega looks like the W, but the only thing is it's kind of rounded, all right? So we call that theta per time. That's angular velocity. Now, if you want to look at linear velocity, let's call this linear velocity. We'll call it V. It's going to be distance per time, right? So the only difference is we're measuring in different units. We measure distance in feet, miles, meters. We measure theta in degrees, radians, rotations, revolutions. All right. So that's that. Now, there is a relation between linear velocity and angular velocity. Okay. If you've ever been on a merry-go-round, has anyone ever been on a merry-go-round? It's kind of like an old school thing. They don't have them on playgrounds anymore. But the most exciting ride on the merry-go-round was when you were on the end of the merry-go-round, hanging on for dear life, right? White knuckling it. If you ever stood right in the middle of the merry-go-round, you could stand there and actually it would be kind of boring, right? But if you were towards the end, you go flying off. This Scorpy. Oh yeah. Hi. Yes. Yeah. Okay. All right. Thanks. All right. So here's the idea. Let's say you have something that rotates, and here's the center. Let's say it's rotating this way. Okay. If you have something that's right here versus something that's right here, they're both going to have, we'll call this A and B. Okay. X sub A and X sub B, they're going to have the same angular velocity, omega. Okay. They're on the same platter. Think of it like a record that spins, right? Every point on that record is going to make one rotation in the same amount of time, right? So they all make one rotation for the same amount of time. But the further out you are from the center, the further you have to go in that same amount of time. The circumference is larger, right? So the distance that you travel around the curve, the arc length is bigger. And the only way to travel a greater distance in the same amount of time is to go what? Faster. Very good. Time travel, faster. So we have a relation between the linear velocity V. Now we can call it linear velocity even though it's around a curved path. Okay. So linear velocity around a curved path, it's going to be directly proportional to the angular velocity by way of the radius. Okay. So that's another formula that you need to memorize. So the bigger, if angular velocity is the same for everything on the record or on the merry-go-round, the bigger the radius, the bigger the linear velocity, right? So the further away you are from the center, the faster you have to go, right? And that's why it was always more fun to be on the outside of the merry-go-round because you were going faster through space, even though you're all making the same rotations in the same amount of time. Okay. So whenever, if you look at like a record player, depending on the size of the record, there used to be a little switch that you can adjust it to spin like either at 78 RPMs or 33 1/3 RPMs. RPMs stands for what? Rotations per minute or revolutions per minute. Your engine spins. And some of y'all have a tachometer in your car that measures RPMs times 1,000 usually, right? And that tells you how many revolutions per minute your crankshaft is turning. Okay. So let's do example 7 real quick. I'm going to jump ahead. Let's say I have a 12-inch diameter long play record. It's called LP, long play, as opposed to an EP, which is a little bit shorter, extended play. All right. We used to have to play the LPs at 78 revolutions per minute. If you played it too slow, it would sound like, and if you played it too fast, it all sounded like Alvin and the Chipmunks album. Okay. But when I was bored in the Rio Grande Valley, I used to go out and get those big old fire ants. They were huge, like 1 inch long, and I would tape them down to the record, and I would just play the record. And then I would play it for a while, and then I'd untape them and watch them kind of walk off and like fall over like they were drunk. And I was like, ha ha, I wish I had friends right? So, so every ant that I taped down on the record was spinning at the same angular velocity of 78 RPMs. Omega was 78 RPMs, revolutions per minute. We can stylize it as RPM. The P is for per, but it's really revolutions divided by minute. So that's the same angular velocity. What I want to know is what is the linear velocity of each ant traveling around the circular path if I tape them down 1 inch from the center, 3 inches from the center, and then on the very end, 6 inches from the center. So what we're going to do is we're going to take out our equation. Linear velocity is R times angular velocity. All right. Now I'm trying to find V. So let's just plug in the first radius, tape it down 1 inch from the center. So that's 1 inch. Now, the units have to match. So when I multiply it by angular velocity, that's 78 revolutions per 1 minute. Okay. I want to get my linear velocity in feet per minute. Okay. So the units are specified, feet per minute. Well, my unit of time is good. I have minutes for time. But what I need to do is I need to get rid of inch revolutions and convert it to feet.
1 foot is 12 inches, so that'd be.
Well, let's go ahead and do this. We're going to use dimensional analysis. I'm going to put this over 1. We're going to have to convert inches to feet, and we're going to have to convert revolutions to a unitless measure of rotation called what? Radians. Okay. And it doesn't matter the order. Let's do the inches first. I'm going to put inches down here, and I want feet to appear. So 1 foot is 12 inches. That's going to get inches divide out. And then I want to get rid of revolutions, and I want radians to appear. So 1 revolution is how many radians? 2 pi. Very good. And now revolutions will divide out. And now if you go through and take inventory, what are you left with? You're left with feet in the top and minutes in the bottom. Is that the units we want? Feet per minute? Yeah. And the radians that are left in the top, they're unitless, right? So now all you got to do is type it in. You don't even have to worry about the ones, because anything times 1 or divided by 1 is itself. So we'll pick up the calculator and we'll do 78 divided by 12 times 2 times pi. Okay, I'll do it with you. Don't worry about the ones. 78 divided by 12 times 2 pi. I get, 40.840 or 8.1 feet per minute. So that ant, that's 1 inch out from the center, every minute it's going to travel a distance of about 41 feet, but it's not in a straight line path. Oh, no. It's in a circular path, which reminds me, we're having our meeting after school today with the sponsors for Spring Fling. And of course, on fun night, we do the bat spin. And this just reminded me of the bat spin. What makes the bat spin so fun? It's the same thing that when I untape the ants to watch them walk off crooked and spew their formic acid all over the place. Same thing with the bat spin. They get dizzy because their distance that they're traveling in feet is not on a straight line path. It's around a circular path. They get dizzy. Okay. Now, if I tape it down 3 inches from the center, what's going to change in my calculation? Let's copy this. Copy. Paste it over here. Yeah, the only thing that's going to change, the linear velocity now is still R omega, but instead of 1 inch, it's what? 3. So here's what we could do. Go ahead and store that value on your calculator. Store it. Just hit stow as X, and you got 40.840 stored as X. All right. We don't have to type this all in again. If we want, we can. Just hit times 3 now, or 3x. What do you get? 122.522 feet per minute. So that's its linear velocity. 122.522 feet per minute. So in 1 minute's time, it's going to travel about 123 feet, but no, not in a linear distance, in a circular distance. It's moving faster. In fact, it's moving 3 times faster than the ant that's taped 1 inch from the center. And then finally, if I tape the ant on the very, very edge, you can paste it right here, right? The linear velocity is still r omega, but instead of 1 inch now it is 6 inches. So take your x and multiply it by 6. So type in 6x and you get 245.044 feet per minute. Okay, so it's moving fast. So there you go. Linear velocity is directly proportional to angular velocity by way of the radius. The bigger the radius, the faster the linear velocity. So anything that's spinning on a record or a merry-go-round, they all have the same what velocity, regardless of where they are on there, linear or angular. They all have the same angular velocity, right? They're all making the same number of rotations per unit of time, but depending on where they are, they have different linear velocities. Now, let's do one last thing here. Feet per minute is grand and everything, but you know what? We have a finer appreciation for linear velocity, not in feet per minute, but in miles per hour, don't we? Oh, yeah. So with that number still in your calculator on the previous line, let's go ahead and set up our dimensional analysis to convert from feet per minute to miles per hour. All right. I'm going to get rid of the feet first. So I'm going to put feet in the bottom and I'm going to get miles to appear in the top. All right. No, 1 mile is, to be culturally literate, you need to know how many feet are in a mile. 5,280.
Why do you have that random?
You need to have that memorized too, Brady. Well, now you do, because you're going to need this on the test, and I'm not going to give it to you. Because I'm telling you right now, you need to be culturally literate. We live in America. You will need this conversion for the test, and I'm not going to give it to you. 5 to what? Tomatoes.
Oh, I see. 5
Oh.
2 H O 5.
Oh, 5 tomato. Oh, there you go. 5 tomatoes. Okay, there you go. Now, Brady, I'm not asking you to memorize it in bananas, okay? That would be also American, I guess. All right. Washington. So that gets rid of feet, and I have miles, and now I need to get rid of minutes. Now, for minutes, I'm going to go through, well, straight from minutes to hours. And Brady, you have to know this too. I'm sorry. 1 hour is 6. Yeah, so you know that without complaining.
Yeah, it's the time frame. You're always dealing with time.
You're always dealing with distance as well.
No, you're not.
You drive now.
That doesn't mean I know the exact distance between my house and the school. And
Well, you do now know how many feet are in a mile, right? 50 tomatoes. Okay. So again, look at your units here. What are we left with? We're left with miles in the top, hours in the bottom. That's miles per hour. 50 tomatoes. I like that. That's easy to remember. 50 tomatoes. Okay, good. I like it. So here we go. I'm going to take the previous line in all of its glory, and I'm going to hit divided by 5280 times 60. And I get 2.784 mph, right? That's how we stylize miles per hour. Now, almost 3 miles per hour. That doesn't seem like that's fast at all, right? If you're behind someone in Landa Park on a weekend and they're going that fast, it's like, would you hurry the freak up? At least drive the speed limit 20, but they're cruising, right? But for an ant, that is like booking it, right? Especially when it's around a circular path. You might have heard about this thing called escape velocity for things that travel in a circular path. If they go too fast, they break out of that circular flat path and they fly off in what's called also tangential velocity. They fly off in a straight line. And that's why they banned merry-go-rounds, because those kids at the end would be white knuckling it, and then they'd get escape velocity and they'd fly up on a tangent. They'd go through the gravel and rocks and hit the trash cans and boom, right up against the side of the building. They'd brush off their knees and say, let's do it again. But some people got involved and like, ooh, that's hurting the little children. And so they got rid of them. All right. All right. Let's go ahead and look at example 6 and example 8, because you're going to have a multiple choice question like example 6, and you're going to have a multiple choice question like example 8. All right. And these are the last two we're going to do. All right. Number 6. Find the angular velocity in radians per second. Okay. Angular velocity, again, could be any units like rotations, degrees, radians per unit of time. So I'm specifying. And the linear velocity in inches per second of the tip of the second hand of a clock that's 5 inches long. So we have a clock, right? We have a second hand. The second hand is this one, and it's 5 inches long. And pretend like we're taping down an ant right there at the very end, at the tip of that clock. We want to know what the angular velocity is and what the linear velocity is. Well, the angular velocity is going to be the same for every point along that, along that tip. So how are we going to figure out the angular velocity? Well, we have to supply our own knowledge of how fast the second hand rotates. The second hand makes one rotation every what? Yeah, we could say every 1 minute, but since I want my units to be in seconds, thank you. We'll say one rotation every 60 seconds. Now, that is a type of angular velocity, right? We would write it like this: 1 revolution or rotation per 60 seconds. Now, that would be in revolutions per second. I want it to be in what? Yeah, let's call that omega, because that is the angular velocity. And all I got to do is convert from revolutions to radians. Miss West? Chris, Miss West needs to see you. I'm recording this, by the way, so if you need to watch it. Oh, after first period. Thank you. Yeah. All right. So 1 revolution is how many radians? 2 pi, right? 2 pi. And look what happens. The revolutions divide out, and I'm left with radians per second. Is that what I want? Yes. So now let's just type it in. Again, we don't need to worry about the ones. So that's exactly what this says, right? So if you want to simplify, get an exact answer, it's going to be pi 30ths radians per second, which might be an answer choice. Or if you actually want to divide it out, what's pi divided by 30? 0.104 or 105 radians per second. Okay. And again, where did we come up with that? We supplied it ourselves from our knowledge of how clocks work, right? If you would have started with 1 revolution every minute, no big deal. You would have just converted revolutions to radians and minutes to seconds as a separate calculation. Dimensional analysis. All right. Now, the linear velocity. Here we go. The linear velocity V is R omega. So that's the third equation that you have to memorize for the test tomorrow. Let's plug in what we know. What's the radius of the second hand? 5 inches. So we're going to put 5 inches there. And then omega, we just found it. I'm not going to use the 0.104 because that's a decimal approximation. I'm going to use pi 30ths or 2 pi 60ths, and that's radians per second. So notice when I write it in there as radians per second, I use the horizontal division bar. Let's see what the units are going to be now. The units are going to be inches radians, which is just inches per second. Is that what I want? Inches divided by second? Yeah. So there it is. If I simplify, I could do 5 divided by 30, math, enter, which gives you a 6th. So this becomes either pi 6 inches per second, or if I want to actually type it out, what would be pi divided by 6? 0.523 inches per second. All right. And that's real, right? So if you taped an ant 5 inches out from the center on a clock, assuming it was Swiss movement and not like, or you know how sometimes they tick, if it was smooth movement, it would be traveling a little over a ½ inch per second, right? So like if you tape the snail there, it'd be like, whoa, right? Or if you could somehow tape a sloth to there, it would be going like, slow down. Okay. So now I could do the same thing. Like tomorrow on the test, if it's not the second hand, if it's the minute hand, no big deal, right? The minute hand makes one rotation every 60 minutes. Very good. Every hour. Or the hour hand makes one rotation every 12 hours. Very good. Yeah, you need to go home and look at your clock.
I'm on like weight of
50 to 80, 52 mate O's. I like it. Okay. Yeah, that's good. I never heard that before. 48 years old am I, and I've never heard 52 Matos. I just had to like memorize it like brute force back in the day. But I had the energy to memorize it because I didn't complain about having to memorize it.
You do realize in this day and age.
All right. Let's go example 8. You're going to like example 8 because it involves Mrs. Lincoln rolling through Landa Park on her 36-inch. Yeah. She drives the speed limit. Okay. Mrs. Lincoln's vehicle has tires that are 36 inches in diameter. Okay. That's the wheel. That's the tire itself. If she's cruising through Landa Park in her vehicle and her speedometer says 20 mph, how many revolutions per minute, that's RPMs, are her tires or wheels making? Okay. Now, here's how we do this type of problem. Instead of using the V equals R omega, we're going to start with the variable quantity. Which of those two values that I give you is the variable? Which one has the ability to change? 20, right? So start with the variable quantity, 20 miles per 1 hour. That's how you want to write it, 20 miles per 1 hour. All right. Now what we're going to do is by a sequence of conversion factors, we're going to end up over here with something revolutions per minute. This is the easiest way to do it. Okay. Now, the thing that's going to be the easier of the two is the time, right? We have hours. We want to get to minutes. So let's go ahead and knock that one out. We got hours in the top. We want minutes in the bottom, right? 1 hour is how many minutes? 60. Boom. So we got our time. Now the fun part, right? You'll like this. We have to get from miles to revolutions. Well, here's how we're going to do it. The first thing we need to realize is her tires are measured in inches, right? So the first thing I have to do is get my units to be on the same level. So I have to get from miles to inches first. Now, to get from miles to inches, Brady, I don't expect you to know how many inches are in a mile. We're going to go from miles to the middleman, feet. Okay. How many feet in a mile? 50 tomatoes, 50 tomatoes. Good. Miles divide out, and I'm left with feet. And now I'm going to go from feet to inches. 1 foot is 12 inches. And now I have inches. All right. And now there's really only one more step. I have to get from inches to revolutions. And this is the magical conversion factor. Because here's what it is. The tire makes 1 revolution every how many inches? Well, it's going to be the what of the tire? The circumference. Good. The circumference. It's 2 pi r or pi d. So if you know that the diameter is 36, the circumference is 36 pi, right? Or you can say the radius is 18, and then 2 pi r would be 2 times 18, 36 pi. All right, that's it. Whatever the circumference of the tire is, the car is going to translate down the road by that amount in 1 rotation. So 1 revolution is 36 pi inches. And now the inches divide out. And what are my units? Revolutions per minute. Is that what I want? Yeah. Now be careful. When you divide by 36 pi at the end, be sure to put it in parentheses, right? We had that conversation. So here we go. You don't have to worry about the ones. We'll go 20 divided by 60 times 5280 times 12 divided by parentheses 36 pi, close parentheses, and I get the answer to be 186.741 revolutions per minute, which is approximately 186 or 187. I think tomorrow on the test, I think I round to the nearest RPM. That's not that bad, right? It's just dimensional analysis, bless you. So as long as you know the magical conversion, getting from inches to revolutions is by the circumference, you can do this. Now there's a variation of this problem where we tell you how many revolutions per minute the tire's spinning, and you find out how fast she's driving down the road. And it's pretty much the same thing. You start with RPMs and you just do your conversion factors. The key is to make sure that the units divide out from high to low. So there's 3 minutes left. Work the test from 2014 tonight. You don't have to turn in 5.2. Here's what you have to know for tomorrow. You have to know S equals R theta. You have to know the area is 1/2 R squared theta. You have to know that 5280 feet are in 1 mile. And now you have to know V equals R omega. All right. I'm not going to give any of those to you. And that's it. It would be cool after the test to do the next example because we figure out how fast we're moving through space. Galileo's birthday is today. He had the heliocentric model that we orbited around the sun. We are moving through an orbit around the sun pretty fast while we're spinning. We're on like the greatest carnival ride of all time called Planet Earth. Maybe after the test, we'll figure out how fast we're moving through space. But that's all you need to know for the test, okay? Clear your calculator, turn it in. I'll be here today during my conference. I have a meeting after school, but I will be back here tomorrow morning. And it should be a fun test. If you can do the 2014 test, compare it with the key, and the free response is very, very similar as well, okay? You should make 100 on tomorrow's exam, and I would love to reward you with 100, all right?